Welcome back, everyone. In this video we're going to be continuing with the idea of the derivative function, but instead of the intuitive graphical interpretation, we're going to be defining it rigorously. And thinking back even further though, we've already talked about how to find the derivative of a function at a point. And we denoted that as f prime of a, and the way that we found that was the limit as h approaches 0 of f of a plus h minus f of a all over h. And this gave you the slope of the tangent line, or the instantaneous rate of change, at one particular point. And as we talked about in the last video, if we find the derivative at a point for every single point of a function, and bring all those derivatives together, we can create an entirely new function, and this is called the derivative function. Now the way that you go about computing these two things is exactly the same, except the interpretation is different. The derivative of a function at a point is a number, because it represents the slope of a tangent line, and the derivative function is just that. It's a function. It's not a number. It's a brand new function. Even though the process of finding the derivative function is the same as finding the derivative at a point, I still want to run through one example. So let's find the derivative of the square root function. And to start, we know that the derivative of a function is the limit as h approaches 0 of f of x plus h minus f of x all over h. And this is just the definition from the previous slide. Now from here, to find f of x plus h, we just take x plus h and plug it into the function. And so that's the square root of x plus h, and then minus f of x, which is the square root of x, and then still all over h. And right now our goal is to simplify this fraction until we can get rid of the h in the denominator, and then we can plug in 0 for h. Now to simplify this, we're going to have to use the technique of multiplying by the conjugate, and so we're going to multiply by the square root of x plus h plus the square root of x. Now if I multiply that in the numerator, I also have to multiply that in the denominator so that I keep this fraction the same, and really all I've done here is I've multiplied by 1 in kind of a funny looking way. Now when we multiply the numerator by its conjugate, we get the two terms in the middle that are opposites of each other, and so they simplify to 0. And as you might recall, this always happens when you multiply something by its conjugate. And then the other terms we have are root x plus h times root x plus h is x plus h, and then negative root x times positive root x is negative x. Now in addition to those middle terms simplifying to 0, we also have a positive x and a negative x, which will also simplify to 0. And all I get left with in the numerator is h. And then I have an h in the numerator and an h in the denominator, and h over h simplifies to 1, and leaves me with the limit as h approaches 0 of 1 over the square root of x plus h plus root x. And now that I've gotten rid of that h in the denominator, I can now plug in 0 for h, and I'll get 1 over root x plus root x, which is 1 over 2 root x. And this here is the derivative of the square root of x. And notice how my answer has an x in it because, as I've said before, this is a brand new function. Now the overall process of finding the derivative function is always going to follow the same format. You're going to start with the same limit and have the same goal of simplifying the fraction until you get rid of h in the denominator, and then you can plug in 0 for h. Now the algebraic techniques that you use to simplify the fraction might look a little bit different, but the overall process will always be the same. While we're here, this is a good time to mention some alternative notations for the derivative. And so far I've been writing the derivative as f prime of x, but could also write that as y prime if I'm using the equation notation instead of the function notation. Now what you see there in the middle, the way that I would say that colloquially, is d dx of f of x. And what this means is the derivative of f with respect to x. And all that's doing is clarifying what the independent variable is. Because later on there could be equations or functions that have multiple variables in them, and they're saying take the derivative of the x variables. And another way that I could write that is dy dx or df dx. But for now, when you see these, they all mean the derivative, and you should go through that process that I showed you on the previous slide.